All right. So let's start with number 11. And I want to make a couple of comments. Now, this first section is mostly like the gateway test, right? On 1 through 14, up until the table, up until number 21. This is what we're talking about for the gateway test. So we got to be able to do, right? That's what we got to be able to work on. So on number 11, I think, is that the one with ln? Ln of 4x squared plus 3x, or just 3? All right, now we need to talk about this chain rule where we say do the derivative of the outside, leave the inside alone, multiply by the derivative of the inside. Right? That's what we said the chain rule means. Now, on some functions, it's easy to tell the inside, the outside, and sometimes it's you get too caught up in what that means. I mean, the outside, the inside. For example, I've seen a lot of people have come to me today and asked me about this problem, and they've written this as their function. Okay, that is wrong. Okay, now I know what you're thinking. What you're thinking is the outside function is natural log, ln. So you do the derivative of ln. Well, what did we say the derivative of ln was? 1 over x. Now, what you guys should have said is when I just said what's the derivative of ln, what you should have said instead of 1 over x, you should have said, oh wait, Mr. Clark, what do you ln of what? That's what you should have said, right? There is no such thing as just ln, right? It's ln of something, right? It's sine of something. You know, that we get that bad habit in trig class where we talk about sine squared plus cosine squared equals 1, and I do it myself, right? And sine, where does sine equal 1/2, that kind of stuff, right? We talk about the function without the input part of it. Well, sometimes that really gets us in trouble, and this is one of those times, okay? So people were thinking, well, do the derivative of ln, which is 1 over x, then leave the inside alone, so that's that part, right? And then times the derivative of the inside, which is that. Well, so we put that in words to help us make sense of the chain rule, but we got to be careful. I mean, that's just an aid for understanding the chain rule. So we got to, that would not be what we need. So what we're really talking about when we say this, when we say ln x, the derivative is 1 over x, what we're really saying is that ln, that when we have ln of some stuff, right, that the derivative is what? 1 over the stuff. And now, actually, because we've learned this thing called the chain rule, it's 1 over the stuff times stuff prime. There you go. I like the way you think, right? Stuff prime, right? That's what the rule really is for natural law. What? That's what the rule really is for natural law. And actually, we're going to write our rules that way. Now, we're not going to put stuff, but we're going to use the letter U. Now, I told you yesterday that I had that's a good one. Yesterday, I had this, on our class website, I told you I was going to give you the derivative rules, okay? So on this website here, and there's a link to this on Google Classroom, and there's, whatever, on Cardicat. Some of you, if you've never been there, that's great. I guess you've never gone, never needed it, but whatever. So on today's homework page for Wednesday, December 3rd, right here I've got this PDF, derivative rules. And so you can have that electronically printed off if you need it, whatever. So you have access to this. I've also shared it with you. You might have got an email about it. I shared it with you on Google Classroom or whatever. So you may have got an email about it as well. But basically, the derivative rules, now we're not going to take time to write these down right now, but it's just a PDF of all these kind of handwritten out. So let me just run through them real quick. So we talked about what happens if you add or subtract two functions. You just do the derivatives individually. If you have a number stuck on the outside of a function, it just hangs out there while you do the derivative. We've talked about the product and quotient rules the last couple of days. Okay, yesterday we learned this thing called the chain rule, right? Derivative of the outside, leave the inside alone, times the derivative of the inside. Okay, and then now here's how we're going to write our rules for all these other ones we've learned. Instead of thinking of the power rule as x raised to a power, okay, since we rarely get just x raised to a power, usually we have some stuff raised to a power. So what we're going to do is we're going to write it this way. So if we notice I say with respect to x here, right? So the u is just representing the stuff. There's some stuff raised to a power. Well, when you do that derivative, we're going to bring the power down in front. We're going to keep the stuff. The power will go down by 1, and then we'll tack on the derivative of the inside, the derivative of the stuff prime. So in all the rules, you'll see this u prime here tacked on to the end. And all that is just talking about the chain rule. It's just saying, all right, so if we got, so this is how I'll talk about the power. So when I say what's the outer function, we say what's a power? Or it's an e raised to some stuff, or it's the ln of some stuff, right? That's the outer function. So e to the u, we always said derivative of e to the x is e to the x. Well, not now. Now the derivative of e to some stuff is e to that stuff times the derivative of the stuff times the u prime. We used this one yesterday when we had 2 to the sine x, right? We had 2 raised to some stuff. Well, the derivative of that is 2 to some stuff times ln 2 times then the derivative, we had sine in there, derivative of sine is cosine. So some stuff. Okay, and we just talked about this ln u one, right? You got ln of some stuff, the derivative is 1 over that stuff times the stuff squared. And there's the rest of them, log, sine, cosine, tangent, right? I was asked yesterday, when do we need to know these rules? Tangent, now, right? We need to know them, right? So we got to be studying them. You got to be studying these rules. So there's tangent, cotangent. So we've taken notes on all these. Now I've written them a little differently now, and they're all on this sheet that I've shared with you. Okay, here's secant is secant times tangent, cosecant. The only 3 we have yet to learn are the 3 inverse trig. We're doing them tomorrow. Arc sine, arc cosine, arc tangent. Okay, so those are out there for you. We won't take time today to just sit here and write them all down, but you can, you will have access to all of those. But when you look at them, notice that that's what I'm doing with that u. All right, so I didn't want to go in and complicate things too much yesterday with all of that, but it might have helped you say on one like this. Okay, so what we need to be doing on this one is doing 1 over 4x squared plus 3, and then times the derivative of the inside stuff, which is 8x. Now, I'm fine if you leave it like that. Normally, though, you would probably put the 8x on top, and you would have that on the bottom. Okay? All right. Another comment I was going to make, a few of you said on number of 12, it's 1 over a square root of some stuff, right? That's number 12. Now, of course, you're going to write the stuff down there is 1/2 power. But I would avoid doing a quotient rule on one like this. The quotient rule is something we have to do sometimes, but if we can avoid it, we should avoid it. And here's what I'm going to say to you. If I have 1 over x, I'm not going to do a quotient rule on that, right? Or let's say it's 4 over x, right? If I got 4 over x, I'm not going to do a quotient rule. I'm going to write that as 4x to the negative 1 and do a power rule. And if I've got x over 4, I'm not going to do a quotient rule on that. How can you write x over 4? 1/4 times x, right? So anytime I have a constant either in the top, that's all I have on top is a constant, or all I have on the bottom is a constant, then don't do a quotient rule. Rewrite it, bring this up this way, or you take the 4 that's on the bottom and write it out there as a fraction, and then don't have to mess with the quotient rule. The only time you should do a quotient rule is when you got some x's up here and you got some x's down here. That's the only time you should do the quotient rule. So on this one, I would take all that stuff and make it to the negative 1/2 power, and then do your derivative from there. Bring the power down in front, drop the power by 1, leave the stuff inside, and then times by the derivative of the stuff on the inside. Okay, that's how you'd want to do number 12. Now, if you do the quotient rule right, it'll still work, but the problem is what people do is they don't do the quotient rule right. When you go to do the derivative of the top, the derivative of 1 is what? 0, which then multiplies and wipes out half of the quotient rule anyway. So, but what happens is people put a 1 there. They forget to make the derivative of that 0. And then it gets messed up. All right, so that's my suggestion. Any other questions up until number 21? Yes. 15. What's the function of 15? The original. You didn't write it down. Cosine. Yeah, now, how do we read that? That's a great question. Really, that should be cosine of x cubed, quantity squared, or all squared. That's how you should read that. If you read that cosine squared x cubed, I guess you can, but again, that notation is unfortunate. What you need to do then is you write this as cosine of x cubed, like Jacob was saying, and then you square that whole thing. That's how you need to write this. So this is one I was talking about yesterday where we can have a function inside of a function and then put that function inside of another function. So it's kind of a double chain. But all you have to do is take your time and follow what we said the chain rule says, which is do the derivative of the outer function. What's the outer function here? Something squared. The stuff squared. So we're going to take the something that is squared. So we're going to bring the 2 down in front. We're going to leave the something on the inside alone. And we're going to drop that to a 1. Right? Times the derivative of the inside. Let's do that in black. So this part is black. This is the inside. So now I need to do the derivative of the black. Well, how do I'm going to put a big set of parentheses. It turns out I'm not going to need them, but oftentimes we would. So now I'm ready to do the derivative of that. Well, how do you do the derivative of that? Well, it's got an inside and an outside. So the derivative of this is the derivative of the outside would be negative sine, leave its inside alone, and then times the derivative, run out of colors, the derivative of that inside is 3x squared. Now, I step back and I look at what I have, and you got to be careful. Anytime you got a power on the outside, you can't be mixing things in with it, but it's just a 1, so it doesn't matter. Okay, so really what we have is this times this times this times this, like A times B times C times D. So we can rearrange and put those, mix them all around. And we want to, because this negative and this 3 and this 2 all need to go together and make a negative 6. And then we have cosine x cubed times sine x cubed. And on the gateway test, that's the answer I'd want to see. Sine and cosine can be in either order, doesn't matter. But that's what you would know. And I think if you type that one in your calculator, that's what it is. Did I leave off something? Oh, yeah. Okay, let me say that again. This is not the answer I'm going to see on the gateway test because I forgot the x squared. There. Right here. The derivative of this inside. The derivative of this. So we start with the derivative of the, here's the thing. You do the derivative of the outside. You leave the inside alone. And the last step is you do the derivative of the inside. Sometimes when you do the derivative of the inside, that takes a while. Sometimes the inside is a complicated thing. And so you have to do quite a bit of work just doing that last part. And that's what happened here. The inside was cosine of x cubed. And so it took a fair amount of work just to do that last part. Okay? Then we put it all together. Anything else? And don't forget your ability with the calculator to kind of check and see what you're doing. But we're gonna definitely be doing more. Thursday, Friday, Monday especially are really focused on just what's on the gateway. Do this derivative, do this derivative. We have a few new things to put in today, tomorrow yet, but we're going to be. Today's homework has a part of it where we're starting this process of just practicing these things over and over again. Okay, which we really need to do. All right, well, let's move on here. I want to talk about 21 just briefly. We were talking about this. This is the one with the table, okay? Now, on the table, they tell you that H, and again, some of you are having trouble with some of these because you're just not writing enough stuff down, I think. I mean, and again, my theory on some things is write down what you need to. Now, if it's worth points, and we've talked about it over and over and over, you sure need to write it down. But if you're having trouble getting it one way, then then try something different. And I think writing it down really helps. So here's h of x. You're given that. Here's h prime of x. So the first entry in the table you have to find is h of 1. Well, I like writing down h of 1 because that tells me, oh, a 1 is in place of that x. So I need a 1 in place of that x. So this is f of g of 1. Okay? So what do? I look at the table for g of 1, and it's a, what was it, a 4? I think it's a 4. So I'm going to place a 4 in there in place of g of 1. So now what's f of 4? And you look, and it's a 3. And so there you go. So that's that entry. Now, on h prime of 1, you would do the same thing. You would put a 1 in place of this x. Okay? Well, what's g of 1? I think it's a 4. Okay, we just said that, didn't we? And then here's g prime of 1. Well, what's f prime of 4? 4. And what's g prime of 1? 3. And so that makes 12. Right? That makes 12. And then you repeat that for 2 and for 3 and for 4. You do h of what? 2, h of 3, h of 4. Right? But that's how you find those values. Plug those in. All right. Now we go to number 22. Now this is the one we talked about right at the end of the period yesterday, where we said that the inside stuff is kind of a mess. Right? You do the derivative of the outside, which is f prime. You leave the inside alone. And then you times by the derivative of the inside. Well, the derivative of the inside is a quotient rule. You have no choice. You got x's on top, x's on the bottom. So quotient rule says derivative of the top, g prime, leave the bottom alone, minus top left alone, g of x times derivative of the bottom, which is 2x, all over the bottom square. So you got that big mess of a thing, right? That's h prime of x. Well, then the question asks for h prime of 1. Well, h prime of 1 means put a 1 in for x here, which means put a 1 in for x there. Put a 1 everywhere there's an x. And then just find those values. I think they gave them all to you, didn't they? Didn't they just give them to you? Sometimes they give you a graph, sometimes they give you a table, sometimes they just give them to you, right? Maybe you got an equation you can put them into, whatever. So g of 1, I think, is a 2. I don't remember all these values. I think that was a 2. G prime of 1 was a 4. G of 1 was a 2. So you got 8. So you get 8 minus 4, which is 4. 4 over 4 is 1. You get f prime of 1, which I think was a 7. So the whole thing comes out to be 7. Okay, so I like how they do this in the book. Matter of fact, 15 years ago, the AP test kind of changed how they asked some of these questions. These things never used to be asked like this. When I was in high school, when I was in college. It was all this other stuff that we're doing for Lifelong Gateway, just crank out derivatives. But then they kind of went to doing more of this stuff. And our book was one of the first books that ever did this, even before the AP test changed. I really like it because it really makes you think about the rules and think about what you're doing. And it makes you use graphs and tables and all those other things. So I really think it's good that we got to do those. Okay, let's talk about 26. Okay, 26. You had a graph there of f. Now, you got to read the directions here. You got a graph of f. But they ask you when g prime of x is 0. For what values of x, it said, is g prime of x 0? That's like asking where does g have stationary points? Well, where does g prime equal 0? Well, this is what g prime is right here. Right? We got to do the quotient, or the chain rule. So where does that equal 0? Well, the zero product property, which you use when you do factoring, says that when two things are multiplied and get 0, one of them's got to be 0. So write it out. So this has to equal 0, or this has to equal 0. Well, that one's easy. Divide by 2. So there's one place where g prime would be 0. And then we got to do this one. Now, this was kind of strange. And it's because of that x squared that fouls you up. I know that. So let me put that in a blue little ellipse here or something. I don't know. Let's circle that in blue. And let's just forget about it. So the question is, because if I'd asked you this, you wouldn't have had any trouble. Look at the f graph. Where is f prime of x 0? At 2, right? When x is 2. In other words, f prime of 2 is 0. You all agree with that statement? F prime of 2 is, oh, I should have my colors again. I hope this doesn't confuse you. All right. So in other words, this piece in here has to be a 2. f prime of 2 is 0. So therefore, in this problem, x has to equal 2. But that's not what we have inside there. We have x squared. Right? Oh, I'm so confused. I didn't know what color. So what we need, so we know, you guys just got done telling me that f prime of 2 is 0, right? On the f graph, the slope is 0 when the input is 2. So that means that this here has to be that there, right? So what's that mean? That means x squared has to equal 2. Well, when does x squared equal 2? Plus or minus root 2. So there are our 3 solutions to that question. Where does g prime equal 0? At these x values right here. Because you have to put in plus or minus square root of 2, then you square it to get an input of 2. Okay, so that's a little different. We haven't ever seen anything quite like that. We're just used to saying, oh, at what x value, at what input is it? Well, at an input of 2. But the problem is our input isn't just x now. Our input is x squared. So we got to think about it a little differently. All right, and then that leads us right to number 31. Now, if you had trouble with 29, 29 is a lot like what we just did there, and it's a lot like what we do on 31. You have to first write, so like on 29, you got this f and g graph. I think I got them up here. You got this f graph and this g graph, right? And they ask you to find h prime of 1 or h prime of 2 or something like that. Well, so you have to do h prime of x, so it's a chain rule, and then you have to plug values in. Well, you get the values off the graphs. Instead of having them in a table, you're going to get them off the graph. Now let's do 31. In 31, it's the same problem we were just doing. They want to know when h has stationary points. Well, h has stationary points when h prime is 0. Well, here's h prime right here. So that's going to be 0 when one of these two things is 0. So either f prime of g of x is going to be 0, or g prime of x is going to be 0. So this is just like number 26. So we solve those two things and we'll have our solutions. So let's go to the pictures. All right. So the first one, f prime of g of x has to equal 0, and then the other one, g prime of x has to equal 0. Okay, well, let's do this one first. That's easier. So when is g prime 0? There. I don't even know. Let's just call it in half. I'm not sure. Looks like it's closer, but whatever. That's good. So x equals -1.5 and 2.5. So there's 2 of our answers right there. All right? Now what about this one? Well, it's the same thing we were just talking about. Let's ignore this red thing on the inside here. The question is just, when does f prime equal 0? Well, there, maybe there. It's kind of hard to tell, but it looks like it flattens out there. So we'll go with it. We'll count it. I probably wouldn't count it if you didn't include that. But so what we want is this red thing to either be a 0 or a 2 or a 5. We need the input to f prime to be a 0, a 2, or a 5. Which means what? We need the red thing to be 0, 2, or 5. So we need g of x to be 0, or we need g of x to be 2, or we need g of x to be a 5. Well, when will g of x be a 0? There, and there, and there. Right? Because that's what we're asking is, when's the output of g a 0? Right? When is it? It's like we were asking there. When is the output of x squared a 2 in the last problem? The output of x squared is a 2 when x is a plus or minus square root of 2. Okay? So this would be at -4, at 1, and at 5. So there's 3 more answers. Okay? When does g of x equal 2? At those 2 places. The output is 2 at -3 and at 0. So there's a couple more answers. And when does g of x equal 5? It doesn't. So never. So there you go. 1, 2, 3, 4, 5, 6, 7 different answers for that. Okay, so that one you really had to extend yourself a little bit. That was quite different than maybe some things we're seeing. But once you go back to it and you think about what it was asking, I mean, it's not too out of the question. It just haven't seen. All right, so let's go ahead and move on then and get some talk about what it is we have to talk about today. This is kind of, while you're getting ready here, I'll just talk about this a little bit. This thing we're going to do here is a way that we have to do derivatives on some special types of situations. Okay? And this will be on the gateway test. There won't be very many of them. Probably one for sure, and no more than two. Most of the gateway tests will be like, here's y equals some function. You do y prime, you do the derivative, follow the rules and simplify it and whatever. And that's it. But there will be a couple on there, one for sure, that says to use implicit differentiation. Now, differentiation just means to do the derivative, right? If we say differentiate this function, we're saying do the derivative, right? That's what differentiation is, the act of doing the derivative. Implicit comes from the term implied, right? Something's implicit is that it's implied. It's not overtly or explicitly stated, but it's implied. Right? So I've listed the difference. So on the left is an explicitly defined function, which basically means the y is by itself, right? The functions we're used to seeing are explicit functions. So like one of the homework questions, one of the first homework questions, they say, write this equation explicitly for y in terms of x. All they're saying there is get y by itself. So that's what we're used to seeing. Now, sometimes we write f of x, sometimes we write y. Those are really interchangeable. Right? F of x equals x squared minus 2x, y equals x squared minus 2x. That's an explicitly defined function. It's right there, plain sight, right? What the function is. An implicitly defined function is where the y is not by itself. And the second one that I wrote there under implicit, you can't even get the y by itself if you wanted to. On the first one I wrote, we could get the y by itself. We could subtract the x squared, divide by 3. We could take an implicitly defined function and write it as an explicitly defined function. Okay? But sometimes you can't. And that's why we need this thing called implicit differentiation. Okay? Now, even when we can't get the y by itself, this would make some sort of an ellipse, like a rotated kind of an ellipse thing, is what this would look like. But even when we can't get the y by itself, we know that x is our input and y is our output, right? It's implied that y is the dependent variable. Now, none of these theorems are you ever going to be quizzed on or anything, okay? But we call x the independent variable because we can plug anything we want in for. It's independent of anything. We just plug anything we want in for x. And then the y, what we get out, is dependent on what we put in for x. Okay, so we call them the independent and the dependent variable. All right, but the idea is here is it's implied that y is the output. Y is in terms of x. So this goes back to what we were talking about the other day about the dy over dx and the with respect to. And this is really important. All right? Because when I do this derivative over here, when I tell you to do this derivative, you don't even ask me generally with respect to what, right? If I say do the derivative of this, right, that's not very good directions on my part, but it hasn't mattered really up until now. So when I say do this, what I'm really saying is do the derivative of y with respect to x. That's why your calculator uses this notation. Maybe why I should make you do it. Every year I say I'm going to make you guys use this notation instead of y prime. Every year I decide not to. And usually it doesn't matter, but then there come up times where I'm like, well, But that's what that means. That just means a derivative of y with respect to x. Okay? So when I say do, and we showed the other day on the calculator how it would give you 0 sometimes if you put different letters in. Well, that's because it treats them as constants if it's not the variable that it's with respect to. So on this one, when I say to do the derivative of this, we always just write down y prime. Right? Well, that's because what we're doing, what we're technically doing is doing the derivative of both sides of that equation. I've never said that to you before. But like in algebra class, when we add 2 to both sides, or divide both sides by 3, right? That's kind of what we're doing here. We're saying do the derivative of both sides of this equation with respect to x. So what's the derivative of y with respect to x? Well, it's dy over dx. It's y prime. But if I ask you to do the derivative of x, what would you say? If I just said to you, I forget we even talked about this stuff. If I just came and say, hey, everybody, what's the derivative of x? You would say 1, right? You would say 1. Nobody would have said x prime, I don't think. Now, until we start talking about this, right? But what's the derivative of x? Well, the derivative of y is y prime, right? What's the derivative of x? Well, it's 1. But in Leibniz notation, the derivative of x would be this. Derivative of x with respect to x. Well, that looks like 1, doesn't it? And it is, right? So that's why we don't write x prime, because that would it's just 1 with respect to x. But remember a while back we talked about a particle moving along the number line, and it was something like this, something like that. What's the derivative of this function? What would you write? You would write x prime here, wouldn't you? Why? Because you're doing the derivative with respect to t, right? So you're doing dx dt, dx over dt. It's with respect to t. So there we would write x prime, right? We would write x prime because we're doing the derivative with respect to t. So this idea of what we're doing the derivative with respect to is becoming important, and so we got to pay attention to it. All right, so back to this. So we do the derivative of this side with respect to x. It's dy dx or y prime. This side is just normal. It'd just be your normal derivative because it's with respect to x. All right, so now we go on to ones like this. Well, how does that affect something like that? So let's take a look at this scenario. If I gave you this equation right here, okay, let's just say I gave you that equation right there, okay, and I said, let's do the derivative of both sides with respect to x. Now, you would say, why don't you just divide by 3? Because normally we would, right? On your homework, they're going to give you some of those. They're going to give you part A. They're going to say, write it as an explicit function of x, which means get the y by itself. So you divide everything by 3, get the y by itself, and then just do your normal thing. And then in part B, it'll say, now do it with implicit differentiation. Implicit differentiation means don't get the y by itself. Just leave it the way it is. And just do the derivative of both sides. So let's do that. So what's the derivative of this side with respect to x? What's the derivative of 3y? Well, think about it. What do we do when there's a number sitting out front? Just leave it. And then what's the derivative of y? Y prime, right? Because we're doing the derivative with respect to x, right? So the derivative of y is y prime. All right, and now let's do the derivative of the other side. What's the derivative of this side with respect to x? 2x minus 1. Yeah, when we're doing the derivative of x's with respect to x, we just do normal. It's just normal, right? The derivative of y with respect to x is y prime, or dy over dx, if you want to write it that way. Now, we should solve that. We don't want to stop there. We want to find y prime. That's the directions. Find y prime. So we're going to divide by 3 now. So we get y prime equals 2/3 x minus 1/3. And that'd be our final answer. That's the same thing we'd have got if we'd have just divided by 3 originally and then done our normal way. But I want to give you simple examples to see what you get. Okay, so the derivative of 3y with respect to x would be 3y prime. All right, now, what happens if, let's look at this page right here. Oh, I just did that one. I forgot I wrote that on this page. Okay, so I meant to go to this page next. So let's go back here. Let's do a few simples. So what's the derivative here? So if I just said do the derivative of this, what would you write? Y prime equals 1, right? It would just be assumed that you're doing the derivative with respect to x, right? So it'd be 1. And on this one, y prime would be 1. I think in this, don't overthink it. In this one, if I gave you y equals t, we would just assume that it's a function of t, right? That we're doing the derivative with respect to t. So we would get 1. And what about this one? Y prime equals 1, right? All of these, the derivative would be 1. Now, this is where that Leibniz notation kind of shows the difference, though. Here, y prime is dy over dx. Here, y prime is dy over dt. And here, y prime is dy over dz, right? You're doing the derivative of y with respect to, and then that input variable. And if it's y equals, and there's only one letter over there, then that's the input variable. So it's easy, right? I mean, that's just what it is. All right. So then we get into these ones that are a mixture of x's and y's. So we just did one kind of out of order here. So we just did this one, and we talked about that. Now you get one like this. Now this would be messier. We could get the y by itself here, right? We could get the y by itself here. We'll do that at the end. Okay, we'll do that later. But let's talk about this new thing we've just mentioned. So let's just leave it the way it is. And let's do, but again, and we understand that what's the input variable here? X. This is the input variable's x, the output variable's y, right? I'm not going to mix a bunch of other letters in there and make you guess. It's going to be x and y, all right? So y is the output variable, x. So we're doing the derivative with respect to x, right? We're doing the derivative with respect to x. And so our answer, when we get our answer, we want y prime. We want dy over dx, right? That's what we're looking for. We're doing the derivative with respect to x. So the right side's easy, so let's do that first. What's the derivative of the right side? 12x squared plus 2, right? That's a derivative of that side with respect to x. What's the derivative of y squared? What'd you say? I hear 2y prime. Not 2y prime, it's not 2y prime squared, but you're getting close. There's no square root, right? Because you're bringing the 2 down, right? I agree with that. It's not 2y prime. It's not 2y double prime. It's not just 2y. Well, if you take little bits of all those answers, you can get some, except for y double prime. If you take little bits of all those answers, it's there. Okay, let me give you a little hint. Let me give you a little hint. All right. So we're trying to do the derivative of y squared, right? That's what we're trying to figure out. Remember earlier we were talking about f of x or y, they're the same thing, right? F of x is the same as y. Agree with that? Right? I mean, they're pretty interchangeable. They're the output kind of thing. All right, so let's look at it that way and see if that helps you. So let's say we had written it that way instead of y squared. Now, let's say we just learned the chain rule yesterday. So let's say I had given you this and said do the derivative of that. What would you have written? Whoop, not plus. Wouldn't you have done that right there? Wouldn't you have said do the derivative of the outside, bring the 2 down in front, leave the inside alone? See, that's the part we were forgetting. When you guys were saying 2y prime earlier, we were forgetting the part about leaving the inside alone. We bring the 2 down in front, we leave the f of x alone to the first, and then we tack on the derivative of the inside. So what should this have been? This should have been 2y, y prime, is what that should have been. Now, I would like for you, when you're doing these problems with the y, this implicit differentiation, I'd like for you to remember that it's chain rule and this is why it is and so forth. But if you can't, you don't have to. You can't, and I don't like doing this, but I'm going to give you just a short little memorization thing you can do. When we're doing implicit differentiation, when you're doing the derivative of the y's, do it like normal, and then tack on a y prime. That's what it is. Because, I mean, think about it. That's what the chain rule is. Do it like normal, bring down the 2, leave that alone, whatever, and then tack on the derivative of the inside, which our inside is our y. Think of the y as like some stuff, right? X is our input variable, and y is what, if we could get y by itself, we'd have y equals a bunch of stuff. So y is a bunch of stuff. So if what we're doing when we do y squared, we're doing a bunch of stuff squared. We just don't know what that bunch of stuff is. So we're doing a bunch of stuff squared, so the derivative would be bring down the 2, leave the bunch of stuff, the y, and then tack on the derivative of the stuff. That's what it is. Okay? So you can just think of it that way. Whenever you're doing the derivative of y, do the normal derivative, tack on a y prime. So what's the derivative of sine of y? Cosine of y times y prime. What's e to the y? E to the y times y prime. Exactly. Just do the normal derivative, tack on a y prime. All right? Because you're doing it with respect to x, right? All right. So, and we don't have to do that with x's, right? If I have x cubed, I don't want people saying, well, that derivative is going to be 3, oops, not equals, but that derivative is 3x squared times x prime. I guess you could, but what's x prime? What's x prime? 1, right? Because it's with respect to x. So x prime is dx over dx, which is 1, right? So we would never tack on an x prime when we have x's, as long as it's with respect to x. I say that now in chapter 4, we're going to do a situation where we actually will be tacking on x primes. Why? Because they'll be with respect to t. It'll be another variable. It'll be like that problem I was saying with the motion. It'll be x with respect to t. And so it'll be appropriate to tack on an x prime there, but not when it's with respect to x. All right. So this is just, again, this doesn't change anything we've learned with all those rules and all the derivatives, product, quotient, all that stuff. It's just kind of this extra thing that when we can't get y by itself or don't want to, we got x's and y's mixed together. This is how we find y prime. Okay? And we go through and we find it. Now let's take a look at this problem here that we just had up here now. Okay, so where were we at? Right here. Okay, so the derivative of y squared is 2y y prime. Now remember, what we need to do here is get y prime by itself. Okay, so we always got to finish now by getting y prime by itself. So we need to divide by 2y. So we're going to get y prime equals, now when we divide by 2, what happens here? 6x squared plus 1, and then be over y. So there's our answer we got right there. Now, that's interesting. When you do implicit differentiation, sometimes you have x's and y's in your answer. Okay? Now, remember what I told you that this is going to be like, I don't know what kind of graph this is going to be, some weird thing. But these implicitly defined functions often are not functions. They do not pass horizontal line tests. But they still have slopes. They still have slopes, so we still need to be able to calculate their derivative. But what that means is when we plug in values, we might have to plug in both x and y's to get their slopes. Okay, which is no big deal. If we know the x value we want the slope at, we'll just put it into the original, get the y, and then plug those values in. All right, but you wouldn't have to do it on the gateway. You would just stop right here. You would just stop right here. Now we said, let's go ahead and let me get a new page here. All right, so what do we got? We said y squared equals, what was it, 4x cubed plus 2x. Okay, so we just did it by implicit differentiation, and we came up with y prime equals 6x squared plus 1 over y. Is that what we had? All right, now let's do it explicitly. That is, let's get the y by itself. Because a couple of your homework problems are going to do that. So we would do the square root of both sides, which means we do plus or minus, and then I'm going to put that to the 1/2 power, because we know we're going to need that anyway. Okay, so let's say I would have said, well, let's go ahead and get the y by itself here. Let's go ahead and get the y by itself, and then let's do the derivative that way. So we go ahead and do that, and now let's do y prime from here. All right. So what do I do? Bring the 1/2 down in front. This would be 4x cubed plus 2x left alone. So the negative 1/2 times parentheses. Derivative of the inside is 12x squared plus 2. Right? Now let's do some rewriting of this, rearranging, because we're going to want to compare it to our answer over here. Right? I think is what we want to do. I think on the homework, I don't think that you'll have to do that necessarily. Some of them are almost too hard to really compare, but this one's not. So what I'm going to do is I'm going to take this 1/2 and I'm going to multiply it over here with that, because that'll work out nice. What do you get? 6x squared plus 1. Okay, so that takes care of that and the 1/2. This part is a negative power, so I'm going to move that down to the bottom. And I'm going to put the plus minus down there with it, just for the heck of it. And so this negative power is going to go to the bottom. Then it's a positive 1/2 power, which of course is a square root, right? So I'm going to write that as a square root. Now I've told you you don't have to do this, but I want you to see something here. Now, is that the same as that? Let's do the same. Because y, here's y right here, right? Y was plus or minus the square root of that. That is y down there, right? Because we just solved for it right there. So yes, those two are the same. This one is just in terms of x. This one has x's, y's in it. But actually, so then when you think about it, which one was easier? Well, implicit, once you get the hang of it, implicit was actually easier in that case. Okay? They give us the same answer. So then it's like, well, if you can do it the regular way, why even learn about implicit differentiation? Well, sometimes we can't get the y by itself. Okay, so we're going to do one more problem here for practice here. Let's do, here I've got one with a parabola, but I'm going to skip over that one. We're going to do this one right here. Okay, so while you're writing that down, so what have we learned? What we've learned is if we got a mixture of x's and y's, we might be able to get the y by itself, explicitly, get the y by itself and then do a normal derivative. Or we might just leave it the way it is with the x's and y's all mixed together and do this thing called implicit differentiation to find y prime. Now, one of the gateway tests probably looks something like this. Now, the reason we need implicit differentiation, because in this one right here, you could not get the y by itself no matter how hard you tried. You could get the y's on one side, you could factor out a y, but you'd always have a leftover y because of that y squared. You could not get the y's by itself in this relation. So the only way to find, and this would be some sort of ellipse, so if we wanted to find the slope at one of the points on this ellipse, we could not do a regular derivative. We would need implicit differentiation. So here's how we do this. We do the derivative of both sides. So let's start on the left. What's the derivative of 5x squared? 10x. Normal derivative when it's the x. We're doing the derivative with respect to x. All right, now here's where we got trouble. What's going to happen right here? Now, I'm going to give you a little bit of help here, and I'm going to group the -6 with the x. Well, no. 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 Soon they forget. We learned this on Monday. -6y plus. There you go. It's negative. What are they missing? The people are not following you guys that said it. It's the product rule. It's the product rule because what we have are two functions multiplied together. We have -6x, which is a function, times y, which is also a function. It's some stuff, right? The y is some function of x. You have to do the product rule. Now, to help you, now the product rule has a plus in it, and so anytime there's a negative in front of a product like that, I'm always going to attach that to the first function so I don't have to worry about distributing it through. So this is like my u and my v. So the derivative of -6x, okay, listen now, listen. The derivative of -6x is -6, we leave the y alone. Plus, I'm not going to write the plus sign yet, but it'd be plus the -6x left alone times the derivative of y. What's the derivative of y? Y prime. That's where that comes from. It's a product rule. We've got to do it. Okay? And so that's one of my favorite ones to put on the gateway test. So you have to remember that product rule. All right? Plus, what's the derivative of 5y squared? 10y, y prime. When you do the derivative of a y, do the normal derivative, tack on a y. Like that first one we just did, I said, what's the derivative of y? You all said y prime, which is great. That's what you should think about. Now, if you want to think of what's the normal derivative of y, it'd be 1. It's like the derivative of x is 1. derivative of y be 1, tack on y prime. So it's y prime, okay? But derivative, normal derivative of 5y squared would be 10y, tack on a y prime. All right, and then what's derivative of 16? 0. Don't forget to put 0 over there. If you put 16, then you mess up all the good work you did on the other side, right? Derivative is, we're doing the derivative of both sides, so derivative of 16 is 0. All right, now, we got to get y prime by itself. How do we do that? Yeah, well, yeah, we got to move stuff. In other words, if I had this, listen. If I had this problem, right, and I wanted to solve for x, we'd get all the x's on one side, and we'd get all the non-x's on the other side, right? That's what we would do. We would gather the x's together. The non-x's would go to the other side. So that's what we're doing. So if I want to solve for y prime, I'm going to leave the y primes here, and I'm going to get the non-y primes to the other side. So negative 6xy prime plus 10y prime. And then on the other side, this would be negative 10x plus 6y. Right? Now what can I do? Take out a y prime. And this will always work because anytime you have more than one y prime in the problem, which you're going to have anytime you have more than one y in the original problem, anytime you have more than one y prime, or more than one y, whenever you do the derivative, you're going to tack on a y prime. So you'll have multiple terms that have y primes on them. Then what you want to do is gather those over to one side. And once you do that, they'll all have a y prime on them, so you can factor out the y prime. Then last thing is we divide. Well, not the last thing because we need to simplify, which sometimes you can, sometimes you can't. But you end up with that. Now that's not where we want to stop because what else can we do? Factor out a 2 and cancel. Factor out 2 on the top, 2 on the bottom, and cancel. So it would be negative 5x plus 3y on top, and it would be negative 3x plus 5y on the bottom. So it's not uncommon for that look in an implicit differentiation to have a mixture of x's and y's in your answer. Okay? And you can make these up all day long. I mean, just like what I did. I just made that one up, as a matter of fact. And so, you know, just have some terms that have x's in them, have some terms that have y's. As a matter of fact, you get creative. Instead of just powers, put an e to the y in there, or a sine y in there. Say that again? No, because if you take a 2 out of here and a 2 out of here, then it cancels. So then, okay? All right. So here's your homework. Your homework is the 3-point. I'm going to add a little bit to it here. Okay, so the 3.3 homework only has a short number of problems because the book does not have a whole bunch of practice for these implicit differentiations. So I picked out the ones it had, which is only 6 or 7 probably. And so we'll do those, and on the website, and I'll show you in the coming days, there's some places you can practice these some more. Okay? But so I want you to do the 3-3 homework. So those problems, those are all implicit differentiation. And then I want you to do any 10 that you want on page 195. Now, 195 is that page where there's just a whole big page full of functions, and you have to do the derivative. So it's just practice. And so over the coming days, every day, that'll be part of the homework. We'll be just, pick out another 10 problems or get on the website or whatever. So when I come around, it'll be just like, you can show me, okay, here was homework, and then here's the 10 practice problems. Now, you might want to do more than that as we get going into it, especially. But, all right. So we're beginning this process of reviewing and practicing chain rule, product rule, quotient rule, all the things that will be on that gateway test. Tomorrow we'll just add those 3 last rules on arc sine, arc cosine, arc tangent. And then that's pretty much all the new stuff. Third Friday will be just practice problems, practice time maybe for you to work. And then Monday is a lot of that too. I mean, I'm sure I'll be working some problems for you and giving you ideas about simplifying and all that. Okay? All right. Okay, so tomorrow, tomorrow would be, let me show you again on that website. So tomorrow there's the 3.4 line. Right, that's the inverse trig rule.
And then another 10.
And then some more on page 195. And then if you look at the assignment sheet, the next line on the assignment sheet is just that page 195. Which I put that, but it's just gonna be, just pick some, just do. Yeah, so
Basically do
I
the ones that
put
have
4
on.
through 60 multiples of 4, they're just like, but yeah.
So pretty much the ones you haven't already done.
Yeah, just keep practicing. Now, the other place and the other thing we'll be talking about is practicing on the website links I was mentioning yesterday.
Right.
And I don't know if you remember that, but that was under the web links here.
Yeah, I wrote that down in my notes.
Okay. Yeah, and I got derivative practice 1, which is where you can, that quite nasty, you can put those where you had the different levels,
Chandra and I are planning homework parties.
Oh, right.
at our hotel room.
And then this one, so she's gone starting tomorrow too.
Yeah.
So I haven't been on these for a while. They're PDFs. Let me look at this. So practice test 1. So they start out pretty basic. Then there's some quotient rule. This one you could actually simplify. You could split this apart, like this over this would be 1, and this over this, that kind of thing. But then this one you can't, so you'd have to do a quotient rule. So I'm looking at this one. So this looks like it's pretty much just algebraic kinds of things. And so that's good. But then I think this one then gets into some trig, maybe more, some ease, gets into more product rule, chain rule kinds of stuff. So they start getting a little harder. Now it gets into some signs, some arc signs. I was thinking there was one. Oh, there's a bunch of them here. So that one's a good one. And then it must be this last one. It must be this last one that has. Okay, here.
Where are you guys going? For?
So all weekend?
Yeah.
Who else is going?
Danny, myself, Joseph Rathenstein, Brandon Zimmerman, Paige Johnson, Shannon Nelson, Morgan Freer, Jesse Vasquez. And Josie's
So there's a couple in here, like this number 9 right here is an implicit. It's got a mixture of X's and Y's. There's another one here. So, and here's another one. But there's another good one right there. So it's got some of those in there. But some of them are a little harder than what we would do. But that one we just got to do is a good one to practice.
Okay.
So, all righty?
Got it, thanks.
UAV? Yeah. What happened to UAV? Cut the program. They cut it? Full eligible. They're like 75. And they just cut it?
That video
See that?
That's 500.
That's scary stuff.
On this one,
That's a new program.
so you had 3y. Would that be the?
No.
Is it 3y prime? Okay.
Because think about it. What's the normal derivative of
More than a
3y?
president cut. They didn't
What's the
say
normal
something.
derivative of 3x?
They're from other
3.
sports.
So the derivative of
See,
3y would be 3
Football.
tack on a y prime. Yeah.
Football is the most expensive sport by far. It's the most money. But you can also make the most money. You're not making money. And, like,
Senior tight end.
Courtney,
everything's better than